Good morning, everybody. My name is Leandro Cordova, and I work with Dr. Perez at the GCREC. And I came to present you guys today the low volume spray technology for control of major diseases of strawberries in Florida. Two diseases that play an important role in strawberry production in Florida is the botrytis fruit rot and the anthracnose fruit rot, caused respectively by botrytis cinerea and Coleoptila multifida. And the most suitable weather conditions for both disease development are leaf wetness duration greater than 12 hours for both diseases, and temperatures from 59 to 77 Fahrenheit for botrytis, and 68 to 86 Fahrenheit for Coleoptila multifida for anthracnose. Both are really destructive diseases that spread rapidly through the field and cause great losses on yield and profit. In Florida, fungicide sprays are the most dependable practice to manage VFR and AFR. And the recommendation, the current recommendation is the use of the Strawberry Advisory System, also known by SAS, which is a web-based decision support system. It's free, it's for growers, for extensionists, for whoever wants to subscribe to the system, and it works with the phone weather database, giving recommendations on spray timing and on the fungicides to be used according with the weather and with the crop stage. The weather mainly with the leaf wetness duration and with the temperature data. And the crop stage is more related with if the crop is blooming or not. Those are the main parameters. For effective control, it's recommended to spray within 48 hours after the alert given by the software. The alert can be a high alert or moderate according with the weather conditions. And also, these alerts given by cell phone texting and by email. Currently, the traditional methodology to spray the fungicides to the field is the use of hydraulic nozzles, sprayers mounted with hydraulic nozzles at a flow rate of 100 GPA, 100 gallons per acre. And here we can see a water-sensitive paper. For who is not familiar with this, it's a paper that is yellow when dry and turns blue whether the droplets touch it, blue or purple. And looking at this number and this picture, and also to how wet the plants turn after a spray, it made us wonder if this is really necessary to spray, because it's not really efficient to apply 100 gallons every acre. So we started wondering if this large amount of water is really necessary to cover this relatively small plant, which is the strawberry, with the fungicide. If we are not wasting product running up to the bed or to the ground, if we can reduce the flow rate and still be effective in controlling both diseases, if by reducing this flow rate and having a more concentrated solution, can we reduce the fungicide rate and how it's going to affect the fungicide resistance? And if the low volume technology will increase the operational efficiency. So we set up a trial with the objectives to evaluate the efficiency of reduced flow rates on the control of PFR and AFR, to evaluate the effects of a 25% reduction on the fungicide rate of the low volume treatment, and to compare the operational efficiency among the treatments. Here on the bottom we have a picture of the low volume sprayers, which is air assisted. So we set up the trial at the Gulf Coast Research and Education Center with the cultivar Winter Star. The planting was on October 9, 2014. We did a randomized complete block design with 4 treatments and 4 repetitions. And our plots consisted of 3 beds of 320 feet. And our evaluations, our harvests were done on the 20 plants on the center of the middle bed, the center bed. Here we have the table with our 4 treatments. Treatment 1 and 2 corresponds with the hydraulic nozzle technology. And treatment 3 and 4, we use the low volume spray technology, which is a sprayer mounted with prop tech heads which is our air-assisted technology. And the difference between 3 and 4 is that treatment 4, we reduced the fungicide rate by 25%. And due to calibrations, specificities, the low volume allowed us to go a little bit faster, to spray a little bit faster, 4.8 miles per hour, while the other technology goes 4.5 and 3 miles per hour. And also, the hydraulic nozzles provided a droplet size, a coarse droplet size, about 350 microns, while the low volume provided a very fine droplet size. What made us wonder if wind would be a challenge during the execution of this ride. We did 11 sprays over the season from November to March, following the Strawberry Advisory System's recommendations on the timing and on the products. The products were protective fungicides such as Captain, Tyrant, and also we sprayed most single-site fungicides as Switch, Abound, and Captivate. During every spray, we placed water-sensitive papers in 3 sections of the plants, on the bottom, on the center, and in the top of the canopy. And further, we scanned these water-sensitive papers and evaluate them for the coverage of the percentage coverage using the software MATLAB. Every plot were harvested twice weekly to determine yield and disease incidence from December to April. We did inoculations. We inoculated our plots with diseased fruits of Botrytis cinerea and Polytoxum occultatum in January and March respectively to increase disease pressure. And all the statistical analysis were done using SAS, not the Strawberry Advisory System, the good old statistical package. And BFR diseased fruits were saved for further fungicide resistance evaluations. Here we have our results from the overall data, considering the yield collected from December to April. We see that the 4 treatments were equal statistically in producing in pounds per acre, around 30,000 pounds per acre. For disease incidence, Botrytis fruit rot, the 4 treatments were equally efficient, again, reducing disease incidence. And we had a field next to us, which was planted with winter star, that was not treated, so we could numerically compare with it. And we see that our Botrytis fruit rot in our 4 treatments were about 50% of the BFR of the non-treated field. And again, for anthracnose fruit rot, evaluated from March to April, because that's when the weather conditions is more suitable for this disease. We can see that again the 4 treatments had the same behavior controlling the disease. Here is a single point spray that we did on 11th February because of a high trigger, high disease alert we had from the Strawberry Advisory System on February 10th. And so I just would get in with more details. We sprayed the product Captivate, which is a protective plus a single site molecule. And we can see that wind was not a problem. It was within a ideal range that goes from 5 to 10 miles per hour. So we can see that it was homogeneous among the 4 treatments, so it was not a variable here. Here we have the water sensitive papers that we placed in the center of the canopy, because it's where most of the flowers were, and the flower is our main target in our spray. And in parentheses we have the percentage of coverage calculated with MATLAB. On our right, this table refers to a harvest done 12 days later after this spray. And we can see that even with under high disease pressure, high alert given by the Strawberry Advisory System, the 4 treatments were again equally efficient controlling the disease. For the treatments, we use the full dose of the fungicides. We spend around $218 per acre only our fungicide costs. And for the treatment, which we reduced the dose, we spent $163 per acre, as expected, 25% less than the full doses. And as wind was considered a challenge, we used the FON database, and we did an average of wind speed during the period of the sprays done during our 11 sprays. And we can see that only 4 of the treatments were not within the ideal range that goes from 5 to 10 miles, but only 1 was higher than the upper limit. So it was not a really big deal, the wind at this past season for our trial. And to compare the operational efficiency, we followed some assumptions that we would spray an area of 52 acres, that our 4 treatments would have a tank capacity of 500 gallons, would spray 3 beds at a time, which is a swath of 12 feet, and our mixing and loading operation would take approximately 25 minutes. And then we got the calibrations information for each treatment, and we compared them side by side with our calculations. So we can see that the low volume technology had an area sprayed per period of time 7% higher than our 100 gallons per acre standard. And as expected, the number of loads were 4 times less than the 100 GPA. And because of this, the total hours of spray to spray 52 acres was 4 hours less for the low volume compared to the 100 gallons per acre, because of the less time spent in the mixing and loading operations and traveling from one field to the water pump. As a conclusion, the 2 technologies were equally efficient, controlling BFR and AFR. The treatment with 60 gallons per acre using the hydraulic nozzles was as effective as the others in controlling disease, but because of the calibrations and the equipment we had, it was less effective operationally. Maybe using different calibrations approach or different set of nozzles, we can increase this operational efficiency. And the low volume or area assisted treatments were 7% more efficient in terms of area sprayed per period of time. And in our simulation, it sprayed the same area as the standard treatment about 4 hours faster. We are doing economic studies to compare the cost per acre of the 2 technologies, the price of each equipment, and the fuel we spent for both operations. And our isolates of botrytis area are being evaluated to check if reduced rates of fungicides affected or not the fungicide resistance. Mainly for the fenhexamide, and that we use it, our single site fungicide, and switch. I would like to thank FSGA for providing us the funding to develop this project, Curtec for providing the technical assistance and the equipment, all the people from the plant pathology lab, from the GCREC, and I'll be glad to take any questions. Thank you.